We have a following problem. Find the maximum volume of a rectangular box inscribed in the ellipsoid x squared over 2 squared plus y squared over 3 squared plus z squared equals to 1 with faces of that box parallel to the coordinate planes. So we have constraint x squared plus y squared, x squared over 2 squared plus y cubed squared over 3 squared plus z squared equals to 1. And we want to find the maximal volume. So what we do, we pick point on ellipsoid, and we're going to pick it with coordinates x, y, z. We will assume that all coordinates are positive. So we're going to have constraint g of x, y, and z to make it equals to x squared over 4 plus y squared over 9 plus z squared minus 1. Constraint equals to 0. Function to maximize is volume. Volume is going to be our function to optimize. And the volume is going to be 8x, y, z. Let's write down Lagrange multipliers. Lagrange multipliers will tell us that g of x, y, z equals to 0, and it will be gradient of f parallel to gradient of g. Let's write them down. Gradient of g is going to be 2x over 4, 2y over 9, and 2z. Gradient of f is going to be 8yz, 8xz, 8xy. So we have the following equations. So we have x over 2 equals to 8yz, 2y over 9 equals to 8xz, and we have 2z equals to 8xy. So we're going to multiply the first equation by x, second one by y, and third one by z. So we're going to get x squared over 2 equals to 8xyz. We're going to get 2y squared over 9 equals to 8xyz, and 2z squared equals to 8xyz. 2x squared over 4. Okay. So what we got here from this one is 2x squared over 4 equals 2y squared over 9 equals to 2z squared. So z squared equals 2y squared over 9 equals to x squared over 4. So we'll take that and we substitute into our constraint. So we're going to get z squared plus z squared plus z squared minus 1 equals to 0. So we're going to get 3z squared equals to 1. So z equals plus or minus, but because z is positive, so it's plus 1 over square root of 3. So z equals to 1 over square root of 3. So let me finish it up. X squared over 4 equals to z squared, and z equals to 1 over square root of 3. So x squared equals to 4 divided by 3. So x equals to 2 divided by square root of 3. y squared over 9 equals to z squared, which is 1 over square root of 3 squared. So y squared equals to 9 over 3. So y equals to square root of 3. And we call that z equals to 1 over square root of 3. And again, we picked x, y, and z positive because that was our initial assumption on x, y, and z, that x, y, and z are positive. Now we substitute those points that you found into the equation over volume. Volume was equal to 8xyz, so 8 times 2 over square root of 3 times square root of 3 times 1 over square root of 3. So we're going to get at the end 8 root of 3 and root of 3 cancels out, times 2 over root of 3, so 16 over root of 3. So maximum volume over such box is going to be 16 over root of 3. We're solving a problem, and we have to optimize function f of x, y, z, subject to constraints g of x, y, z equals to 0 and h of x, y, z equals to 0. To apply Lagrange multipliers, we'll do the following. To apply Lagrange multipliers, we're going to say that we need to satisfy constraints g of x, y, z and h of x, y, z equals to 0. And we're going to say that our gradient function of f equals to... So what we want to say is it coplanar with gradient of g and h. So it equals to lambda 1 of gradient of g plus lambda 2 of gradient of h. Let me write down one example on how to do that. So we have a plane x plus y plus z equals to 2. It intersects paraboloid z equals x squared plus y squared. Okay. And the intersection is going to be an ellipse. Find the highest and the lowest point of the intersection. We're looking for highest and lowest point of intersection, so we're looking for function f of x, y, z, which is just z. So highest and lowest point is z coordinate, and we have two constraints. G of x, y, z is x plus y plus z minus 12, and we have second constraint, h of x, y, z is going to be x squared plus y squared minus z. So first constraint is essentially saying our plane, x plus y plus z minus 12 equals to 0. Second says it's paraboloid x squared plus y squared minus z equals to 0. So we're going to find gradients. Gradient of f equals to 0, 0, 1. Gradient of g equals to 1, 1, 1. Gradient of h equals 2x, 2y, minus 1. So from here, so we're going to write the following equations. First coordinate of gradient f equals to 0 times 0 equals to lambda 1 plus 2x lambda 2. 0 equals to second coordinate, 0 equals to lambda 1 times 1 plus lambda 2 times 2y. And the third coordinate, 1 equals lambda 1 plus negative 1 times lambda 2. From the first two equations, we can get negative lambda 1 equals 2x lambda 2, and from the second one we're going to get 2y lambda 2. Notice that lambda 2 cannot be equal to 0, because if lambda 2 equals to 0, that implies that lambda 1 equals to 0. But that will contradict if lambda 1 equals to 1. So lambda 2 cannot be equals to 0. So what we get is 2x times lambda 2 equals to 2y times lambda 2. So we get x equals to y from here. Taking that x equals to y and substituting that into our constraint x squared plus y squared minus z equals to 0, we're going to get z equals to 2x squared. Now we take z equals to x squared, x equals to y, into equation of a plane, x plus y plus z minus 12 equals to 0, and we're going to get x plus 2x squared minus 12 equals to 0. So we're going to get 2x squared plus 2x minus 12 equals to 0, x squared plus x minus 6 equals to 0, so we're going to get x plus 3 times x minus 2 equals to 0. So we're going to obtain two solutions, x equals negative 3 and x equals to 2. Because x equals to y, which implies y equals to negative 3, y equals to 2. Because z equals to 2x squared, we obtain z equals to 18 and z equals to 8. And it's clear that this point will be the highest point, and that will be the lowest point on the intersection between plane and a paraboloid. So that will be the highest point, and that will be the lowest point.